Hello and welcome back to EC 497 Introduction to Human-Robot Interaction. I'm Professor Carlotta Berry, and this week we will be talking about robot teams. One thing to think about is that although a lot of the discussion will be in the context of heterogeneous and homogeneous mobile robot teams, a human and a robot can also make a team. So always think about this in the context of your final project and the human-robot interaction that you will create between a human, yourself or someone else, and your Blossom robot, and how the topics discussed here can be expanded to relate to that topic. So the objectives for today's lecture are to list metric classes for human-robot teams, review a conceptual model for supervisory control of human-robot teams, compare and contrast the human control and robot control loop, and review human behavior, cognitive and physiological precursors, discuss human team characteristics and features of successful teams, and define swarmish. Metric classes for human-robot teams. Mission effectiveness is the most popular metric for a human-robot team performance, and that makes sense because a robot has to have a task or a goal and a mission. So the most important metric is, will the human and robot work together, be able to achieve that mission? The 4 metrics to measure robot effectiveness include task efficiency, neglect tolerance, robot attention demand, and interaction effort. So human-robot interaction metrics are based upon either the human, the robot, or the system. Human performance involves situational awareness, workload, and an accurate mental model, as we discussed in our previous lecture. Supervisory control is a conceptual model that involves the robot behavior, the human behavior cognitive precursors, and the human behavior physiological precursors, and any type of uncertainty which may be represented as sensors, actuators, display, human uncertainty, odometry, etc. And here's a conceptual model of a human-robot interaction for supervisory control, where here at the bottom you have the local loop with the computer, the actuators, the world, and the sensors, and the robot behaviors in the middle. Then the uncertainty grows as you move towards the mission or the task, with the information shared between the two being the info, the human behavior, and the controls, where the human behavior is problem recognition, decision making, and then implementing some action. And then up here in the mission task, things that could happen is you could have physical fatigue, physical workload, physical discomfort, trust, mental workload, situational awareness, a mental model, emotional state, and self-confidence, which all represent the human states or the human behavior physiological precursors. And then down here, attention resources that the human has to use in that process. Also under supervisory control, you have a human control loop where the operator receives feedback on robot and mission performance and then has to adjust the robot behavior through controls, typically some kind of human-robot interface. In the robot control loop, you have the robot interacts with the real world through actuators and collects feedback on the mission and performance through sensors and perceptions about the environment or the world. From the human behavior, that can be characterized in terms of the problem recognition, decision making, and action implementation. As we said, based upon the mental model and the situational awareness, the human recognizes there is a problem or there's not a problem, has to make a decision about what to do next, and then has to implement something to have the robot execute in that situation. So human behavior, cognitive versus physiological precursors. Cognitive would be mental models for long-term knowledge, situational awareness, which refers to dynamic knowledge, human trusts, mental workload, self-confidence, and the human's emotional state. Physiological precursors would be fatigue. The human's been working a long time and is tired. Physical discomfort, sitting for a long period of time, or physical workload. There's so much that has to be done. So that could also cause problems in a human-robot team that has to achieve a mission or task. So team characteristics could be membership in a team can enhance communication, trust, effort, and commitment. And robots in critical domains must coordinate their behaviors with human team members. So robot applications can be divided in 2 broad domains: controlled environments, artificial or real world environments are out in the wild. And these can be unpredictable field applications such as SWAT, military, space, or rescue. So a lot of times a successful human robot team will have a shared common goal, shared mental model, subjugate individual needs for group needs, know and fulfill their roles, and trust each other. So robots should not be considered as human teammates because they lack values, cannot access mental models shared by humans, are not driven by self-preservation, lack the ability to protect themselves, and set false expectations of autonomy, thinking about Asimov's laws in the context of this description here. So here is an example of a robot team working successfully together, where as it recognizes one member of the team has fallen short or changed, the other members of the team will step up. So human-robot interfaces you want to use to develop, debug, and evaluate a distributed algorithm of a physical infrastructure, utility software, light, sounds, and movement. Speaking in terms of a robot swarm, but remember, we're thinking about it also from the context of a human-robot team. So here's another example of a hands-free remote programming where a team of robots is coordinated to work together, where software is downloaded to a gateway robot, and then this robot is able to communicate that information to all the other robots in order to play this music. Hands-free robot programming. Software is downloaded to a gateway robot. This robot uses the radio to broadcast changes to all the other robots. So this would be something where the software would be from the user interface that the human now uses to control multiple robots, but only communicates with one. So here is an example of that type of coordination in order to play music. So having a centralized user interface also allows a single user to control a swarm of robots and send commands to a robot or even the entire swarm team as shown here.
We'll demonstrate a distributed algorithm for routing agents like robots or UAVs around an environment according to fluid-like flows. A motivating idea is that in many situations, instead of directly talking to one another, robots communicate with the assistance of static infrastructure, like wireless routers, cell phone base stations, or air traffic control towers, which are themselves networked. This leads us to ask how we can offload some of the control to the base stations and distribute resulting computations over their network. In our demo, each triangle represents a region in which a particular router has control authority. The routers are virtual, simulated on an Intel Core 2 PC, but the algorithms are inherently distributed so that each router need only talk to its immediate neighbors. The blue edges represent the boundary of the environment through which agents cannot pass. The triangle and quadrilateral are obstacles. The purple lines are the internal edges, across which agents are handed off between virtual routers. Our interface will be a wand with reflective markers, which is tracked by a motion capture system. As the wand is moved across edges, it generates flows across them, which our distributed algorithm projects onto a global incompressibility constraint. Using the wand, we begin to generate flows around the top of the complex. These flows are displayed as superimposed arrows, and whenever they change, the stream function is shown overlaid in false color. By superimposing opposing flows, we decelerate the top and continue down the side. Although most changes are local, small flows are generated throughout the complex. We decelerate the side, and as we move through the middle, robots are drawn in from both the top and the bottom to satisfy the incompressibility constraint. We can continue to manipulate the flows, the robots navigate, avoid collisions, and interact with a human operator by behaving as a fluid.
You can also have a global user output, which monitors actions in the internal state of the robot simultaneously, where lights and sound allow the robot to communicate to the user by speaking swarmish, or in a language which lets it know the health of the team or any individual robot. So swarming shows an example of coordination between multiple robot teams or swarms, but as we said, you could also extend this to how could a human be in the loop with this human robot team, where you could use things such as LEDs for behavior level debugging on individual robots, or an audio system that provides the user with an overview of the activities of the entire swarm, as shown here. And so we see similar to as we did in the previous video that just by knowing the relative position of the closest neighbors, the robots are able to make lines, pentagons, boxes, etc. behind the leader robot. So having a centralized interface, such as a human that has an overview of the entire activity that communicates to each robot what it needs to know in order to execute this activity. So multiple robot HRI design factors. As we've discussed before, things to consider are ease of use, user workload, information flow, software maintenance, and robot maintenance. And here is one other example of commanding multiple robots through an interface.
Rotor capable of agile flight. Multiple vehicles can fly as a formation. We developed a method to transition between formations in 3D. The team can also navigate in environments with obstacles.
You can also have dynamic task assignments, such that a large group of robots will be partitioned into subgroups, and the subgroups will perform different tasks as shown here. And task allocation is two components. Decide how to divide a group of robots into subgroups in order to assign who will do what part and achieve the desired subgroup assignment in the distributed system as shown here. So ideally, the next level of your final project after one team of human-robot interaction could be multiple humans in one robot, or multiple robots and one human, or multiple robots and multiple humans. So you would then want to start to think about things like task allocation or subgroup assignment in order to achieve some goal. Here, these robots are deciding how to divide up in order to navigate around prescribed obstacles in the world, deciding which robots will go left or right, or if the entire team will stay together and clump to get around an obstacle. And this concludes today's lecture on multiple human-robot teams. And please remember to complete the quiz and come back for the next lecture, and have a great day.